Now let's look at the second case where we have 4 factors. Then load data for case with 4 factors. So first of all, we need to load the data. I'll just copy and paste the previous case just to make it easier. Okay. So first we have catalyst charge, and then I need to change the file name 4 factors, and then also, and in this case I also have 16 values because I had only one run. Then the temperature, which is column B, and then B. Then we also have the pressure, it's column C. It's column C. Then we have the concentration, it's a column D. Then finally we have Y value, the yield, and it's a column E. So E. And just to make it clear, I'll just clear everything just to make sure that all data disappear. And indeed we have like 16 by 1 value. Then if you look, for example, at C or at Y, so you can see the values. Okay. So first of all, let's look at the Y values. Plot for Y. Then you can see that figure plot Y values. You can see that again the Y values look fine. You see some groupings, but it's okay because we have some strong factors. But at least we don't have any severe outliers. That's the best. That's the most important thing in this case. Okay. And now again we can make the effect plot very quickly. Figure main effects, and then Y, and then I combine all the factors together. So in this case I can either use a cell array, or in this case I also can combine them as a matrix because they all numerical. It doesn't matter actually. So you can see the main effects. Okay. Then you can see that the pressure is indeed an inert factor, temperature has positive effect, catalyst charge and concentration have negative effect. Then you can make also interaction effects, but I will skip it. Okay. Now let's look at the how to calculate the effects and make a cuckoo plot for effects. Okay. And in this case, it's a little bit tricky. Of course, we can use the same code as I've shown you before, but in this case, to calculate the matrix for all interaction effects, including the 3-factor and 4-factor interactions, you have to write quite a lot of things, okay? What you can do instead, you can try to use my toolbox. I wrote a set of functions for this DOE course, which you can also use for everydays, like, for example, if you plan your experiment. So let me show you how to do it. First of all, you need to download the toolbox. You can do it for Moodle, so you can see this link here. So just click on it and download the toolbox. And then copy the downloaded folder and unzip it here. So you can see that if I click here, you can see a lot of different functions that always start with DOE. So they have this prefix DOE, then a lot of different functions. And then what you need to do is you need to make it visible for MATLAB. To do that, you click right mouse button, add to path, selected folders and subfolders. Okay. And then if you don't want to do it every time you open MATLAB, you need also to save these changes in path. You click home, then set path, and then simply you can see this path here to this DOE tools, and then simply click save. So now MATLAB will remember the path to all these functions, so you can simply use them. Okay. So what you need to do. So there are 2 functions that calculates the effects. It's getInt effects and getMain effects. Actually, if you open, you can see the code, and then you can see the help. So you can see that you provide design metrics and Y values. First is design metrics, second Y values. And then you will get 2 things. You will get the effects, vector with effects, and the names for the effects. Okay. Then if you look at the second function, interaction effects, again, you provide the design metrics, effects, and then the level, the maximum you want to calculate the effects for. And then you will get the effects and the names for the effects. Okay, let me show you how it works. So first of all, let's calculate the main effects. So main effects, it's DOE. Then get main effects. Then first you need to provide the design metrics. We don't have design metrics, but we can make one, right? So we can make one just by combining all the columns together. CC, T, P and C, because we have numeric values, so it's easy. So we provide this design metrics here, and you provide the Y values. In this case, you don't need anything else. And to remember, it has actually 2 outcomes: the effects and the names for the effects. Okay, And actually, it doesn't matter which style you have, design metrics you have. For example, it can be the real values or -1, +1, or for example 0, 1s. It doesn't matter. And then you can see the main effects and the interaction effects and the names. And the names of the main effects. So these are the effects. You can see -824, -0.25, and -5.5. And these are the corresponding names for. That's the effect from the A factor, B factor, C, and D. Simply the first, second, third, and fourth. Okay. So, and if you compare the effects calculated by this function with what I have shown you with in the learning sequence, you will see that they're absolutely the same. So this is effect from the pressure, which is inert factor, no effect. And then we have two negative effects from the temperature, from the catalyst charge and the concentration. Then one positive effect from the temperature. Okay. Then the same idea how to calculate the interaction effects. In this case, again, you just use the function I provided. You don't need to show any. To calculate anything yourself. You can do it, of course, to practice, but in this case, it's easier to use the inter effects. Then dmy by default. And then by default, it will calculate all effects up to 3 factor interactions. So I'll just show you that. EA, and then disp, IE names. Okay. So you can see that these are the names for the calculated effects, and these are the effects. So you can see, for example, AB has effect 1, then AC has effect 0.75, and so on. And then that's the biggest effect we got, okay? And then you can see it's up to 3 factor interactions. If you want to see up to 4, for example, you just write 4 as a third argument, and then you will see, actually all interactions that are available in this design, at least, okay? Now we can use the calculated values to make a cuckoo plot. Of course, you can make the normal cuckoo plot. You simply write cuckoo plot, and then you combine these two effects together, the main effects and interaction effects together. Then you can, I need semicolon because it's a column vectors. So you can see the same picture as I've shown you before. So you see the most effects are actually normally distributed because they're random, and then we have 4 non-random effects. This is the biggest effect. It's from the temperature. It's 23. Then you can see this is effect. We have also the main effects and interaction effects. But the problem is with cuckoo plot, the normal cuckoo plot, it's a bit difficult to add the names, so you don't see which effect is where. Okay. So I also make a function that makes it a little bit easier. It's called doi plot cuckoo. I will just make a new one, figure, doi plot cuckoo. And then you can see that you need to provide actually values and names. So it's simple. You provide the values, main effects, and then interaction effects. And then you provide the names you also got from the functions, main effect names, and then interaction effect names, right? So in this case, it will show you the names automatically. So you can see, so this is the original plot made by the built-in MATLAB function, and this is the plot with my function. You can see that the points are the same. It's just the only difference is that it allows you to add easily names of the factors. So you can see this is interaction, this is effect from the catalyst charge, this is effect from the temperature, and this is effect from the concentration of the catalyst, okay? So that's one thing, and then just simply to show you this ANOVA with different models, with different effects. So ANOVA. So once again, you remember how to make ANOVA. You just simply run ANOVA n equal to ANOVA n, and then the y values and the groups, I will just combine them as like this: C, C, T, P, and then C. Okay. Then by default, ANOVA, remember the ANOVA makes the model only for the main factors. Okay, so in this case again, we can see all the effects because they're pretty strong, but it's important that you need to take into account all systematic variation. We know that we have at least one source of variation. It's the BD interaction, right? So you can make a model to show all interactions. It's called full. Okay. But in this case, you remember that we don't have any values because we don't have enough degrees of freedom to calculate the random, the noisy part. Why we don't have these degrees of freedom? Because we have only one run for each trial. So we don't have enough variation. All variation is used to calculate the effects. We don't have any variation for the error part. The degrees of freedom for the error part is 0, right? But if we limit interactions only by two-factor interactions, and luckily ANOVA easily can do it by changing full to interaction, then in this case we will have at least 5 values, right? Plus the average, at least 5 values for the calculating the error. So that's we have 5 degrees of freedom for the error part. So we can calculate the variation of errors, the variation of noise, and therefore we can calculate the F value, which is a ratio between systematic variation and the noise variation. So in this case, we will get all the results, and then you can see that we got the same results as in my slide. So we have 0, 0, and almost 0 p-values for these factors, and then we have also one important interaction. It's this one. It's BD interaction. Okay. So this is how to analyze experimental results if you use full factorial design in MATLAB. This is how to produce all necessary statistics and plots and how to explain them. In the next learning sequence, we will talk about how to do the same but for the fractional factorial design.